All right, so let's do another example here. Let's say you've got your TV. TV is here, and somewhere on it, there's a little receiver that receives signal from your TV remote. And that remote transmits infrared signals at 38 kilohertz. That's just a number I found online. I'm not 100% sure if that's the frequency, but let's just say that it transmits IR at 38 kilohertz, and that's how your remote basically tells your TV to turn on, tells your TV to turn off, etc. You're having a hard time getting the TV to come on because sunlight coming through your window is also hitting the sensor with DC. That's a terrible color. Let's switch over to orange. DC sunlight is hitting your receiver as well, and it's drowning out the receiver with some huge DC noise, basically at 0 hertz from the infrared radiation from the sun. And so you need to design a filter for your receiver that will filter out the DC by a factor of 1,000th of the original value. And you want to let the IR signal pass through at 38 kilohertz, okay? And so hopefully we can take this, hopefully you see that we can take a very similar approach where we want to basically, we know we want to pass 38 kilohertz, which is going to be here, 0 dB at 38 kilohertz. And we also want to pass, I guess that's fine. We just want to pass 38 kilohertz. And we also want to attenuate DC by a factor of 1/1000th, which would be somewhere way down here down the line. Let's just go 3.8 kilohertz. 380 hertz. And then let's just go 38 hertz. And then somewhere down here would be like 3.8 hertz. So we're getting really close to DC there. So what we really want is somewhere around here. We want 1/1000th, which is 60 dB. So minus 60, minus 40, minus 20. Zero. So this is the response that we're looking for. Something that looks like this. Right? And so I could design it with my cutoff frequency. My cutoff frequency could be a little bit higher. I could stand to shift this way a little bit, but this will do just fine. So let's just say that this is my signal, or this is my frequency response, and I'm aiming for cutoff frequency of 3.8 kilohertz, which for an RL high pass filter we saw previously was 1/2 pi f L over R, right? And so again, all we have to do is we have to take this equation. We know the frequency that we want for our cutoff. We have to pick a value for either our L or for our R, and then we have to solve for the values, and then that would be our filter. So let's take this equation again and take this over to the next page, and we'll go ahead and do that. And let's say that the only thing that we have available to us in our lab is 47 microhenry inductor. So we have to make do with that inductor, and then we have to solve for the resistance value that we need, okay? So let's do that. And our filter is going to look something like this. It's going to be a resistor here, an inductor here. That's going to give me a high pass response. So we know L already is 47 microhenries. Let's solve for R. Okay? So if I know that that's the case, I can say R is equal to 3.8 kilohertz times 2 pi times sorry, this F is not supposed to be here. My bad. Let me get rid of that here too. I was mistaken. Should look like this. 1 over 2 pi L over R. Okay. So R, I basically have this R in the denominator of the denominator, so I can move that up to the top, and then I'm taking 2 pi L and multiplying it over to the other side. So 2 pi times 47 microhenries times 3.8 kilohertz. Let me plug that in and see what R value we get. 3,800 times 2 pi times 47 times 10 to the minus 6. Oh, I get a really small value for resistor, 1.12 ohms. Okay, that's not very practical. That's a really tiny resistor, so this would not be a great filter, but that is what the math tells us to do. So theoretically, what we would do is if we wanted to design this and we weren't limited to this L value that I picked arbitrarily, we would use a different L so that we could drive this R up to a more practical value and get the same response, okay? And so that's kind of the give or take with these filter designs. Sometimes you might pick a value that's not that results in a value for the other component or components that's not practical, so then you would have to change the other component value. But if you were to throw this into SPICE, you would get the response that you need. It's just not practical to use a resistor that small. But let's just call it a day because this module has gone on for a very long time. And that will be the components for my high pass filter that gets the job done. All right, so I'm gonna go ahead and end this video, and right at the end of this module, we've just got a few more videos left talking about active filters and how we can cascade them to get even more ideal responses. Okay, so I'm gonna end this video right here.